A very good afternoon and warm welcome to all of you in the series of Windows of Opportunities in Science and Engineering organized by Indian National Science Academy and Indian National Young Academy of Sciences Mumbai chapter. So the objective of conducting these kind of weekend webinars or seminar is to empower our student community, researcher community, and those who are associated or even not associated with science and engineering and technology. So just to give you a brief overview, those who were not available last Saturday and do not know about what is INSA, who is INIAS. So INSA is Indian National Science Academy, which was established in January 1935, and the whole purpose or the goal and objective of INSA is to promoting science in India and harnessing its scientific knowledge only for the humanity and the national welfare. So INIAS was founded by INSA in 2014 and again with the objective to promote science education and networking among especially the young scientists at both national as well as international level. So INIAS has currently 80 members and there are many activities and initiatives taken up by INIAS. To give few names like INIAS members do a lot of science outreach camps, remote area lectures, career awareness workshops, webinars on various topics including current pandemic, that is COVID pandemic. We have been doing so many webinars and many more things only addressing to the need of society and to help the society in whatever small way we can. So basically INIAS is actively involved in science communication, science outreach activities, and within this context we know that science and technology has a very big power and it can solve all the world's problems, and also historically it has made the world better. But the problem is, communicating science or the awareness about the science and technology is not there. So INIAS is bridging the gap between communicating that science and bringing a lot of awareness into the common population. Just to give you, this is just two few days back's initiative. Young scientist, that is INIAS, has launched a pronged nationwide mass awareness campaign to boost the myths about COVID-19 vaccination. This has popped up in many news, and this is a very good initiative appreciated by Professor Ashutosh Sharma, Secretary of DST, and our President of INSA, and many other big people who have organized this initiative. So you can find out more details about INIAS on our inias.in website. So within this context, today's talk is on the S in STEM, that is relevance and opportunity. And today we have with us Professor Janvi Punekar, who is from Indian Institute of Technology, IIT Bombay, and she's working at Department of Earth Sciences. Dr. Punekar has a lot of awards, accolades, and she has completed her degree from Geoscience Department at Princeton University in 2016, and previously from 2016 to 17 she was affiliated with ICER Pune, and her area of research is very interesting. Her focus is on studying microscopic fossils and biostratigraphy. Basically those deals with constraining the ages of sediments. I'm sure Dr. Janvi will give us a glimpse and few idea about more about that, because I'm not expert or I have no idea about what exactly that research. Yes, microscopic fossils and few things I am aware, but she will I am sure she will give us a brief idea. But most importantly, Professor Janvi is a very passionate scientist, and who has a lot of passion and liking for sharing the science with the society, doing the science for the society, and most importantly through her talk inspiring the young generation for taking, career opportunities in science and technology. So, Professor Janvi, we are so fortunate to have you today with us on this very platform of Windows of Opportunities in Science and Technology, an initiative taken by INSA and INIAS. So thank you so much, and I look forward for a very active participation from all the participants. And over to you, Professor Janvi.
Hi, am I audible?
Yes, you are very much audible.
Okay. Is my screen visible?
Yes.
Okay. So is it full screen now?
Yes, now it is full screen.
Perfect. Perfect. Thank you, Dr. Shalini, for the great introduction. Yeah, so good afternoon, everybody. Special thanks to the organizers for giving me this opportunity to speak in the weekend webinar series. I think it's a wonderful initiative, and I really enjoyed the previous talk last week by Professor Arpita Mandal, although I watched it later after the scheduled talk. So I'm not completely sure about the target audience, but I'm assuming it includes students who are aspiring researchers and scientists at different stages of their career, and may also include established scientists. So hopefully there is a little bit for everybody in my talk today. So what is STEM? STEM is basically an acronym for science, technology, engineering, and mathematics. So we do talk about STEM a lot, but when you have to formally describe it or talk about it, I was at a loss of words because I never really systematically researched what it was. So thanks to this talk, I got a chance to do that. So the first questions that came to me were, what does STEM stand for? What is STEM education? Why is it important? And what do you do with a STEM degree? Okay, so again, STEM is an acronym for science, technology, engineering, and mathematics, and has many other disciplines under each one of these categories. So if you do a quick internet search, it will tell you that STEM as an acronym was preceded by less catchy acronyms like SMET for the same words, science, mathematics, engineering, and technology, or STEMM, where the extra M stood for medicine, which was also included in the definition. Now, these areas of science are grouped together, science and, well, we will discuss that in a while. So these areas are grouped together because they are related academic disciplines, and yet they are very different in their approach and broader impact on humanity and society. So STEM is important because it's in all aspects of our life. Science, for example, is everywhere in the world around us. The sun that rises, the food that we eat, the air that we breathe, the water that we drink. Technology is also in every aspect of our lives, including the cell phones that we cannot even put aside for a minute. And also this Zoom virtual meeting for this particular webinar, which is made possible by technology. And engineering, which is the E in STEM, is what has given us skyscrapers, highways, bridges, bullet trains, and trips to the moon. Mathematics is absolutely unavoidable in every occupation, even if you dislike it like I used to in high school. So every activity from paying the grocery shop owner to understanding fractals in nature requires mathematics. So it's impossible to list every discipline that comes under STEM areas, but some of them include engineering disciplines like aerospace, mechanical, civil. Also includes astrophysics, astronomy, classical mechanics, mathematics, computer science, biology, nanotechnology, neurobiology, geology, climatology. Everything comes under STEM. But from a learning point of view, STEM is basically an interdisciplinary approach to learning, where academic concepts are coupled with real world lessons. Unlike conventional classroom teaching and systems where somehow learning gets reduced to just imparting knowledge or information and a rat race to get good grades, STEM approach basically encourages students to understand fundamentals and apply them immediately in the real world scenario. And this could be science, technology, engineering, mathematics in various walks of life. So, what exactly is STEM education, which was our question number 2? There is a lot of hype about STEM education these days. It's discussed on all board meetings and educational societies. So, what is it all about? I've myself heard of it so many times since the time of my PhD, and I've also used it in a lot of discussions. But as of yesterday, I learned a lot more about it. So, quoting the National Science Foundation of USA, in the 21st century, scientific and technological innovations have become increasingly important as we face benefits and challenges of both globalization and a knowledge-based economy. I would like to stress on a knowledge-based economy. Again, to succeed in this new information-based and highly technological society, students need to develop their capabilities in STEM to levels much beyond what was considered acceptable in the past. So, basically, most of the conventional educational models that we've studied in, despite having a lot of good students and a lot of talent, this method has limited students from thinking unconventionally, out of the box, again, another word that's used a lot, thinking creatively and in innovative ways. So this is where STEM as an idea or an approach or a curriculum comes into picture. Students generally are extremely curious and impressionable. So instilling an interest at a very early age would actually put them on this path. So research shows that students develop interest in STEM fields on an average at the age of 8. This could be because of introduction to middle school science in textbooks, general curiosity, or the fact that technology and gadgets and gizmos fascinate them at that age. If you spend time with kids under 10 years old, which I do a lot, you'll be amazed at the kind of questions they ask. Very, very fundamental, but extremely challenging to answer in a way that they can understand. So, what happens then? Where the leap from being an observer for the kids, observer of nature, understanding nature, and asking questions, to actually becoming an analytical thinker or a scientist, or for the tech side, from being a user of technology to actually becoming an innovator, rarely happens. And if at all it happens, the transition is very slow. I wonder why. It possibly could be because science and maths are visualized as difficult subjects. There may be a lot of pressure to perform in school, to get good grades, to do better than Sharma ji ka beta, to get a lucrative job that pays a lot, or a lot of pressure on bringing prestige to the family name. All those things which basically squeezes the joy out of learning in school for the sake of learning itself. So by exposing students to STEM education and giving them opportunities to explore science in a multidisciplinary, integrated, hands-on, do-it-yourself kind of way, it might help develop a passion for science and hopefully pursue an eventual career in STEM fields. So one of the biggest challenges to bring in such a transformation in the education system is the infrastructure and the attitudes of people in general. Another challenge could be funding, because schools will require money to change the way they teach in classrooms or outside. Many of the educators, I think, are still, they think that an alternative way of learning might distract students and they may not be able to cover the entire syllabus or all the list of points they need to cover by a certain age. So that kind of takes away from the switch from conventional mode of education to STEM fields. However, in the Indian context, STEM is a relatively new term, although it's catching up pretty fast. So the education sector is gearing up now for smart classrooms, hands-on learning, DIY activities to learn science. There are also in better known institutes and universities, there are tie-ups between STEM companies and industries with schools. So they provide funding for learning centers, for tinkering labs, for innovation and incubation cells. So this encourages students to understand concepts and help solve real world problems. The government is also doing its bit. That's what I read, and there is a lot of funding for transforming in institutes and universities in terms of infrastructure. Government of India has also recently focused on Make in India, which puts a lot of I wouldn't say pressure, but it's a lot of motivation for starting STEM education at a school level and have students participate in this Build in India movement.
Professor Janvi, I'm sorry to interrupt,
Yeah.
but are you changing your slides or it is since...
No, I'm not changing. It's
okay,
just
I'm
questions.
sorry to interrupt. Thank you. Go ahead.
Yeah, so I do have slides later, but I will change them once I'm done with this slide. Okay. So question number 3 in understanding STEM was why is it important? So a robust kind of STEM education creates critical thinkers and problem solvers. And we really need that in the next generation of human beings. So taking into consideration that India is one of the countries that produces the highest number of scientists and engineers, the growth of STEM education has picked up, even though it's new as an idea. The world is changing really fast and getting more complex and competitive, and also ruthless in many ways. So it's more important than ever that the younger generation is equipped with sharp observational skills, critical analytical thinking, sound background knowledge of science, and an ability to apply it to unforeseen situations in interesting, novel ways. So these are the exact kinds of skills that students would learn if you follow a STEM approach to education. So indeed, if we were to face a global apocalyptic crisis, which might actually happen, in fact, we may be in the middle of a mass extinction right now, who knows? These are the very skills that will help us to adapt and to survive and to find ways of being safe. That went a little dark, so I'll come back to STEM discussion. Many countries around the world are now realizing the importance of this kind of education system and are trying to upgrade their way of learning science and technology for that matter. So in some sense, STEM education also helps bridge ethnic and gender gaps, because the kind of jobs that you will eventually get are going to be skill-based, intellect-based, and can be done by anybody who has equipped themselves with this way of thinking. So that's a nice angle to it. So in the end, to round up this slide, what do you do once you get a STEM degree? This kind of education and degrees have direct implications for the country's workforce and overall development. Science, technology, engineering, and mathematics workers play a key role in sustained growth and also the stability of the country's economy. India is the second in terms of STEM graduates per population. Every one individual out of 52 is a STEM graduate in India. So the total number of graduates as of a count made in 2016 was a whopping 2.6 million. So these are the number of STEM graduates we actually had in 2016. STEM graduates have been contributing to the country's economy with well-paid salaries, whether they are settled abroad or they're back in India. The turnaround of Indian economy with comfortable foreign exchange reserves is also because of these STEM graduates doing well. So within the country, according to one newspaper article that I encountered, we are now at a stage where the number of STEM jobs are growing at a faster pace than the number of STEM graduates, which is a very nice thing because we will have jobs. According to the National Science Foundation, again, it's predicted that 80% of the jobs created worldwide in the upcoming decade will require some form of maths or science skills. So there is scope for STEM graduates. Statistics also show that 70% of those with a bachelor's degree in STEM fields are actually not employed in STEM occupation. So it's not the end all be all. You don't have to end up in a STEM field even if you're educated in the STEM approach, so to say. All right, so I think now for a slight change, it's a lot of content for that one. Oh, this rock jumps. I didn't know it was, I wanted it to jump. Okay, so now for some familiar turf, what exactly is science? The S in STEM, this was what the title was, and required quite a bit of brainstorming, but that's what it is. So what is science? To some people, science is that difficult high school, college level courses, which includes physics, chemistry, biology, apparently meant for the smarter kids. To others, science is this thing practiced by scientists in white lab coats, thick goggles, nerdy looking guys holding glass beakers, or handling specialized equipment in labs. If you go to the root of the word, though, science comes from scientia in Latin, which basically means knowledge. So simply put, science is a way of thinking and a way of being. So it refers to a systematic, organized body of knowledge in any area of inquiry that is acquired by the scientific method. If you look at the slide at the very left, I've given a generic schematic of the scientific method. Is someone trying to speak? I just heard somebody. Please ask questions in the middle if needed. Okay, so what exactly is a scientific method? According to T.H. Huxley, as a biologist, natural historian, simply common sense at its best, that is rigidly accurate in observation and merciless to fallacy and logic. So basically, scientific method is a standardized set of techniques and rules of how knowledge must be built. So it includes replicability, which means two people asking the same question, conducting the same experiments must come up with identical, if not identical, similar results. Scientific method also focuses on precision, which means theoretical concepts which are often difficult to measure must be defined with precision such that others can use those concepts. Falsifiability, which basically is a theory must be stated in a way that it can be disproven. So questioning a theory must be possible. And the final point that it focuses on is parsimony, which means if any fundamental observation can be explained by a lot of explanations, the most elegant, simple explanation should be chosen. That's what it means by parsimony. So any branch of inquiry that does not allow the scientific method to test its basic laws is actually not a science. The purpose of science is to create scientific knowledge, which is a generalized body of laws and theories, which may be to explain a natural phenomenon or behavior of interest. Laws are observed patterns of phenomena, whereas theories are explanations for this behavior. So just to give an example, if you look at Newtonian laws, an object at rest will remain at rest, an object in motion will remain in motion. The second law was about stationary or moving objects. What happens when two objects collide? Force is equal to mass into acceleration. So basically, all these laws collectively constitute the basic basis of classical mechanics or about moving objects. So the goal of scientific research is to discover laws and postulate theories. In the end, to build scientific knowledge. So a little bit on a philosophical tangent, we may try to understand the world, and the idea is to arrive at a truth. We may never actually arrive at that truth. We are just trying to reach there. Okay. And there might even be multiple truths. So my own research with the dinosaur extinction event has taught me a little bit about this asymptoting truths. So the theories upon which scientific knowledge is based are only explanations of phenomena. And the progress of science is marked by our progression over time from relatively less awesome theories to more awesome theories. And it's all because of informed logical reasoning. So we arrive at scientific laws and theories based on logic and evidence. Now, logic is the underlying factor for theoretical sciences, and evidence is the underlying factor for observational sciences. And these are the two fundamental pillars that lay foundation for scientific knowledge. Now, observations with poor logic do not lead to good science, and which is why I have the jumping frog here. There's a little anecdote. So a biologist was trying to study a frog, and what he did was cut one of the legs of the frog and say jump, and the frog jumped. He cut another leg of the frog and said jump, and the frog jumped. He cut a third leg of the frog and said jump, and the frog jumped. And he cut a fourth leg of the frog and said jump, and the frog did not jump. So this was a meticulous researcher, and he was making notes at every point, every step of his experiment. But the conclusion he arrived at was, when you cut all four legs of the frog becomes deaf. So that is an example of observations with poor logic. So the two have to go hand in hand. In science, theories or theoretical science and observations, which form the basis for experimental science, are interrelated. They cannot exist independently of each other. So theories provide meaning and significance to what we observe, and observations help validate and refine existing theories, or even construct new theories for that matter. So depending on a researcher's training and interest, scientific inquiry may be either inductive or deductive. You can look at the small illustration that I've put in there to help you focus. So in inductive research, the goal of a researcher is to infer theoretical concepts and patterns from observed data. This is basically the theory building kind of research. The other kind of research is deductive research, where the goal is to test concepts and patterns known from theory using new empirical or observable data. So this is the theory testing and theory refining kind of research approach. So much of my research fits into the second category. So inductive and deductive research are two aspects of one iterative research cycle that keeps improvising itself. So it's important to understand theory building or inductive research and theory testing or deductive research, and both are important for advancement of science. So elegant theories are not valuable if they do not match with reality, and a lot of data is useless unless it can contribute to construction of meaningful theories. So a good researcher would know how to handle both these aspects of science. So conducting good research requires two skills, the theoretical and the methodological. So the theoretical is know what, and the methodological is know how. Methodological skills are what we learn in the lab. This could be how to run a machine or how to run an experiment. And these can be learned in your PhD or in your lab training for masters or bachelors. Theoretical skills, on the other hand, are a little more abstract, and they can only be done by practice and by discussions with people who are already doing it. So in some sense, this is through apprenticeship, and this is where research assistantship comes into picture. All right, so the scientific method, as applied to social sciences, includes a variety of research approaches, tools, and techniques, qualitative, quantitative, statistical data. So we'll come to the difference between natural and social sciences in a bit. Before that, let's talk about types of scientific research. Depending on the purpose of research, these could be exploratory, descriptive, or explanatory. Now, we all do this all the time. I've basically been doing science for the last 10, 15 years of my life, but never really thought about where my research fits into this philosophy of science. So now I know that it's applied. And in terms of exploratory, descriptive, and explanatory, it's more towards the explanatory side. So exploratory is to explore. Describe is to describe observations. Taxonomists do that if you are familiar with biology. Finding explanations for phenomenon is the explanatory part. So in a lot of ways, when we do science, we begin with the exploratory and descriptive, and then move on to the explanatory angle of science. So now science can be class, and this is especially for students who want to know what kind of science they want to do and how science is classified so that they can make an informed choice. Sciences can be classified in a lot of ways. They can be classified based on how science is done or what end goal it has. It can also be classified based on whether it has any use to humanity or not. Okay, so in terms of in terms of branches of science, you can categorize them as formal and empirical. Formal basically include mathematics, statistics, logic as pure, and in applied sciences, this could be computer science, for example. So math basically deals with the study of quantity, structure, space, and change. Statistics is study of collection and organization of data. Logic is study of principles of inference and correct logical reasoning. All right, so in terms of empirical sciences are the ones that must necessarily be supported by evidence, observed or experimental. This is basically further classified into natural and social sciences. Natural science is the science of naturally occurring phenomenon, as the name suggests. This could be about light, objects, earth, celestial bodies, living organisms. So disciplines like physics, chemistry, biology, earth sciences, space sciences, all these come under natural sciences, but the pure kind. In terms of natural but applied sciences, you can apply the basic sciences as engineering, agriculture, medicine, sorry for the typographic error there, medicine and pharmacy. The other kind of science is social sciences. Now, natural sciences were different from social sciences in many aspects. Natural sciences have to be precise, accurate, deterministic, independent of the person making these observations. For instance, a scientific experiment should always yield the exact same results, irrespective of time, place, or the person doing the experiment. Whereas social sciences don't have to have that. So social sciences can be classified into disciplines such as, if you are looking at the pure aspect, economics, political sciences, sociology, psychology. If you want to apply these, then management, business administration, pedagogy are some examples. So this kind of science can afford to be a little less accurate, a little less deterministic, a little less ambiguous. And I don't mean any offense here. It's just based on the nature of data that you have to allow for such ambiguity. So I'll just give you an example. If you want to measure a person's happiness with some instrument that you created, you may find that the same person is happier or sadder at different times, and there is no way of predicting this. So one's happiness may depend on each day, it might be different. And besides, we don't have an instrument to measure it and quantify it. So social scientists are usually better equipped at handling higher levels of ambiguity in data, this kind of uncertainty and error that comes with just the kind of data they deal with. So I think that summarizes the different kinds of science: formal, empirical. Within formal, if you are doing pure sciences, it deals with logic, maths, and statistics. If you want to apply this, some of the areas could be like theoretical computer sciences. Empirical are completely observation based, not axiomatic. This goes into natural and social. Natural sciences, the ones that we study in school, physics, chemistry, biology, earth sciences, space sciences. When you apply this could be engineering, agriculture, medicine, or pharmacy. Social, pure sciences, economics, political sciences, sociology, and psychology. And when you apply these could be applied in fields like management, business administration, and pedagogy. So now it's very interesting to see how science and the way people perceive science has evolved. Another classification of science could be pure sciences versus applied sciences. Now, pure science is where it derives theories, predictions. It's about studying and understanding nature, and to study natural phenomena through observation, experimentation, and the strict use of the scientific method that I just discussed. So the main objective, though, that is where these two differ. The main objective of pure science is to increase the knowledge bank of humanity, to increase what we know about the world. Now, pure science is also called basic science, and it's simply to investigate nature by experimental methods. Applied science, on the other hand, it always has an end goal. It's utility based, and it's about how a pure science or knowledge is useful to humanity. So it's a very subtle difference. It's a difference in what motivates you to do these sciences. If you just want to understand the world, it's pure sciences or basic sciences. If you want to understand in order to solve an everyday problem or some other, a practical issue, then it becomes an applied science. So the former seems to be more of understanding, and the latter is more of a matter of action. So if you to quote G.H. Hardy, if you have read about Srinivasa Ramanujan, you would know who G.H. Hardy was. He is one of those guys who worked with theory of numbers and was openly proud that his work had absolutely no applications whatsoever. So pure sciences. But it turns out that his work did actually become useful in cryptography. So there is really no distinction between the two, and you cannot keep them apart. Pure sciences will somehow have an application. And on the other hand, applied sciences will lead to new questions which will encourage pure sciences. So a little bit of about these pictures of these guys put here. One is, this one is, I think, Plato and his student Aristotle. There is Isaac Newton here, Leonardo da Vinci, and Galileo. I picked these particular pictures because they're all making some weird face, and it just felt interesting to include those. So the development of scientific thought, modern science as we know it, arose about 300 years ago and saw a jump. And approximately this was the time when Newton published his book called Principia. Now, coincidentally, the rate of ecosystem damage and how we have manipulated Earth has also spiked, and it dates back to the same time, which is 300 years ago. The American Association of Advancement of Sciences in the year 1848 has had 461 members, and now they have more than 130,000 people. So clearly there is a rise in science and scientists. So in some sense, if you think about it, more than half of the scientists who have ever lived in the history of humans are actually alive today, which is pretty impressive. So what is it that drove this kind of a scientific revolution? Was it understanding the nature or pure sciences, or was it how it can be applied and made useful? In other words, applied sciences. That's why I've put the picture of Leonardo da Vinci and Galileo. Pretty good example to discuss pure and applied sciences. Now, Da Vinci was a painter, inventor, engineer. He was a genius, but he also developed innovations to help aristocrats in their military endeavors. And, others could give him a problem and he would find solutions. So he was not understanding the world merely to understand it, but he was also making use of it for humanity. On the other hand, Galileo, known very well for his telescope, served the purpose of basically what we understand as pure science. He didn't intend to create a telescope. All he wanted to do was study the stars, the celestial objects, and he needed a means to do that, and he created the telescope. So that is a very nice example to tell pure and applied sciences apart. So the terms science, scientist, scientific method, they're all products of 19th century. Before this, science was viewed as a part of philosophy, and it actually coexisted with logic, metaphysics, ethics, and other branches of philosophy. So the ancient Greeks, and here is where Plato and Aristotle in this picture become relevant. They suggested that the fundamental nature of being and the world can be understood more accurately through a process of systematic logical reasoning called rationalism. Nothing to do with observations. It was just completely thought-based. So Aristotle, who was Plato's student, his classical work called Metaphysics actually suggests that the criterion of truth is not sensory, it's not empirical, it's not observable by the senses, but rather completely brain-based, okay, completely intellectual and deductive. However, in his later years, Aristotle deviated from this ideology and did accommodate empirical sciences as true science. All right, I think there is a lot that can be discussed about the philosophy of science. I don't want to get derailed, so I'll come back to the present. And I hope you understood the difference between pure and applied sciences, because if you remember the story of Da Vinci versus Galileo, or even Isaac Newton, or Gregor Mendel, who did his, I hope you remember from high school biology, the peas experiment that he did. These were all not driven by how these experiments would be useful to humanity. They were just done to understand nature, and that was pure science. Before I round up with this slide and this discussion, I would like to mention that there is, as someone who has done science for the last 10 years, which is not a lot though, I have sensed a certain prejudice against scientists who want to do science just for the heck of it. And that, I think, is a little sad, because you might have a lot of accidental discoveries which will be extremely useful, but you cannot always start doing experiments because there is an end use in picture. So not belittling applied sciences, but you cannot have those without a sound background and encouragement to pure sciences. So this is even in the job scenario, I've noticed that people who have an application to the immediate future of mankind, those projects are better funded. Those ideas are more celebrated than just doing science for the sake of science, which is pure. So now the next question, and this again is addressed to the younger audience who might be in a place to decide whether they want to do science or not, and if yes, what kind of science. There are two questions. Are you cut out for science, and is science for you? So assuming that you have, you do like science, the question is, what skills do you need? What do you need to have to be able to do science? One of the most obvious answers would be a reasonable to high IQ, maybe, I'm not too sure, because some of the very good students and scientists I have seen are not the toppers of the class or the ones who have, very high speed intellect. It's people who are consistent and driven and have a lot of patience are the ones who make better scientists. So yes, you need above average intelligence, but what you actually need is independent and innovative thinking. Can you come up with fresh ideas, or are you stuck in a rut of what other people have done before you? By all means, know what other people have done before you, but repeating it is not doing anything great, right? So you need to have independent thinking, innovative thinking. Are you able to assess the facts thrown at you and evaluate them? Can you critically assess them? Can you think of which ones may be less important than others? And this is an ability that you develop only after practicing science. This is not something that can be taught to you in school. So you should also have problem solving abilities, a reasonably good background in quantitative methods. Even if you hate science, you should. And a lot of motivation to discover something new or want to know what's going on around you. And last but not the least, you need to have a lot of perseverance and persistence, because experiments fail and that hurts and it wastes time and you will feel frustration and anger. So you need to have a lot of perseverance and persistence to actually do science, whether pure or applied. Another thing that you would probably want to actually be good at is time management and communication skills. By communication skills, I don't mean the number of marks you obtain in English or Hindi in your high school or board exams. What I mean is, can you grasp the material that is given to you, truly understand it, evaluate it, and can you reply back, counter an argument, think on it, and express yourself appropriately? So that is the communication skill that you might need to actually do science, because you cannot, however boring writing or giving talks might be, or however anxious it might make you, it's part of the deal, and you have to know how to package and express your science. So the next question is science for you? Because it's a path that is not, I mean, it looks stable, but it's not always, a cakewalk. So you will never have instant gratification in science. You may or may not get instant results. You may or may not get the results you expected. Experiments go wrong. Experimental setups go wrong. So think about it. If you don't have the patience, if you don't have the determination, it may not be for you. Also, science requires a lot of rigor. You need to be disciplined, you need to be strict, you need to be methodical, you need to be meticulous, especially if you're doing experimental science. You cannot afford to just forget which test tube something came out of. I mean, that doesn't work. Also, sometimes you might, you also need to be honest to do science, because you cannot, create data. And if your motivation is getting, I don't know, public appreciation or career milestones, covering career milestones faster, may not exactly drive you on the correct path to do science. I mean, science must be done for the sake of it, which means you are increasing the knowledge base of humanity. You cannot do that by lying your way through it. You cannot create data. You cannot cheat. Okay. So ethics and honesty are also very important in science. So if you think you want quick success, this is not for you. On the other hand, in terms of the job front, you can have a range of salaries if you do science. Some of them are more modest than the others. Some of the applied sciences may get you better industry jobs, may pay you better, you may have a better lifestyle. Science for the sake of science, which is basic or pure sciences, there might be difficulties in getting your research funded or even getting a job that pays you lucratively. But you will get good jobs and you will have enough money to survive. So it's not like you're not going to have anything. So that's another aspect that you would want to consider. However, to summarize it all, I think the kick that you get out of a discovery, it compensates for all the hardships and shortcomings and difficulties of doing science. So what should your, this is again for the students, what should your typical educational trajectory be, especially if you are in India? How would you choose between pure or applied sciences? Especially keeping in mind a long-term career in science. So for science enthusiasts, engineering and medicine may not really beckon. I remember that I was probably in 4th standard, I don't know, sometime long back, when I announced to my parents that I don't want to do engineering and I don't want to do medicine at all. So if you are very sure that that's not for you and you really want to just understand the world around you and how it ticks, then for such people, I think science is your deal. And higher education in pure sciences can be really fulfilling and satisfactory. So what do you do after, let's say, you're 10+2? After 10th, you will clearly choose science, which will include subjects like physics, chemistry, mathematics, biology, either biology or information technology. That used to be the trend when I was in school. So it was either a computer-based subject or a biology-based subject. So clearly you will need a science background in 10+2. And then there are many programs in India that can cater to higher education at a bachelor's level. Now, even for these, the courses that many universities and institutes offer are divided on all the kinds of classifications of science that we've been discussing. So you will either have courses in physical sciences or you will have courses catering to natural sciences. Now, this is not very relevant in the more recent sort of research scene, because everything has become interdisciplinary and you mix and match. So, but however, the courses available at a college level are still on physical and natural sciences. That's how they're classified. So you can either choose life sciences supported by chemistry and physics, or you could have physics and mathematics and statistics as one aspect. So bachelor's courses or bachelor's honors courses are usually, they're offered as zoology, botany, life sciences, microbiology. Sometimes you even have food technology, agriculture, biotech, biomed. So you need to look at the websites of these colleges. You need to look at the teaching staff. You need to possibly interact with people who are graduates from the place, and then choose wisely, because you will waste a lot of time if you make a wrong decision. However, nothing is irreversible, and eventually you can always do what you want. I have a friend who started with BSc in chemistry, and she wanted to do medicine, but 10 years later, I think she's tending towards that. So you can approach your passion in a lot of different ways. There are many paths leading to what you want to do. So how do you choose? I think one of the first criteria for your choice is your own interest. You would have had a flavor of what science is all about until 10+2. So you should choose the courses based on what really motivates you and makes you interested. In my case, I chose geology. It was kind of unconventional at that point of time, but now I think many more students are choosing geology as their specialization. Second thing you need to remember is the scope of the subject. If you're not sure about liking something a lot, then it's better to choose combinations of subjects which will have multiple opportunities in future. Taking physics, chemistry, and mathematics, or physics, chemistry, biology is really safe, because you can specialize in any of these three very wide-ranged fields. The way BSc programs in India work, they're usually 3-year programs, and you might have some good colleges, universities that you could go to. For example, some of the better known colleges, especially in terms of teaching and infrastructure, are in Delhi, Mumbai, Chennai, Bangalore. In Delhi, you have Stephen's College, Hansraj, Hindu College. In Chennai, you have Loyola, Stella Maris, and Madras Christian College. In Bangalore, you have Mount Carmel, Christ University. Mumbai, you have St. Xavier's College. Now, this is not based on ranking or importance. This is just names that I collected. So how do you get into these? Of course, you need a very good percentage, and you also have to have the relevant subjects in 10+2. And some of these may even have an interview system where you will have to clear them. An alternate route to doing science, which is slightly more recent, is the ICER BSMS programs or similar BSMS programs, which are in a 4+1 is equal to 5 integrated programs. And the entry could be multi-channel through JEE, or if you are supported by either KVPI or Inspire Fellowships, or if you're a college topper, 10+2 topper, then you get in. So again, colleges, universities, institutes all have websites with updated information. So when you want to make a choice, I think it's a good idea to visit these websites and maybe make a Excel sheet and maintain all the pointers and compare them before you make your decision. All right, in terms of master's degree, again, I already talked about ICERs, but you can also, you have entrance exams like JAM, which is Joint Admission Test to master's programs. This is in different IITs. You can also go for master's to ICERs. The reason why I keep talking about IITs and ICERs is in terms of infrastructure, these are really good, and also teaching and their course structure. So they equip you to do good science in some sense. After MSc, if you're still into science and you want to really specialize, of course, a lot of people choose to take jobs after MSc, and they can do anything ranging from lab technician to management programs after masters. But if you are passionate about science and you want to specialize, you can do PhD, which could be either in India or abroad. By now, I think infrastructurally, India and these relatively well-known institutes have all the infrastructure that you would find abroad. So you're not really missing out a lot on the science part, but things tend to go slower here. And of course, exposure in terms of, if you want to see the world, you won't get it. Otherwise, I think it's really your call where you want to do your PhD. If you want to do your PhD in India, again, IITs and ICERs are pretty good. You need good grades from your masters, a good CGPA, research alignment, and you need to clear the interviews. For abroad, it's a slightly more involved process. It needs a lot of planning. Explore the universities or the advisors the research groups you want to join, shortlist, organize the information, write to your potential advisors, look for alternate funding opportunities if your advisor doesn't have funding for your PhD. Write a very good statement of purpose. Please don't copy or get your SOP written by somebody, because people can tell whether it's genuine or not. Appear for GRE, TOEFL, IELTS. GRE is for general aptitude. TOEFL and IELTS are language requirements because we are from a country where English is not our first language. So you have to show good numbers in your TOEFL and IELTS. Of course, grades matter. And if you go to the US, typically a PhD is 5 to 6 years, but I know biologists who have done their PhD for 7 years. So it's a really long haul. Unless you are very passionate about your area of research, think twice. After PhD, you can do a 2 to 3 year postdoc and then start applying for jobs. If you go to Europe, it could be a 3 to 4 year PhD. Exceptions exist, of course, everywhere. And you could do a postdoc.
Professor, just sorry to interrupt, but we are running out of time, and you may take another 5 more minutes, and then we will have a live question and answer session.
Sure. So I think I've mostly done. And I will just quickly talk about the career prospects. You could either go to the industry, Now, the profile and job satisfaction depends on yourself and your field. A lot of people that I know who went to the industry left their jobs or were laid off, or crisis like the COVID pandemic would really upset your situation. But if you really like what you do, and if you like the problems that are given to you, then industry is your thing. High paid and timed jobs. Teaching is sometimes thankless, but actually very satisfying, and you have the happiness of mentoring young, bright minds. In terms of research, well, if you continuously want to work on furthering science, then this is what it is for you. Academia is a combination of teaching and research. So you could do both. But based on my own experience, teaching loads can be pretty backbreaking and take a toll on your research. So if research is your primary aim, then you should probably take a pure research kind of a career. So rounding up on what I do, I think I was in 4th standard when I decided that I want to be a paleontologist. Mostly because of this particular scene in Jurassic Park where people were digging up a dinosaur. And I read up about dinosaurs and got fascinated. And then I realized that they don't exist, which led me to study about evolution and extinctions. And I've been very lucky that my parents did not stop me from doing what I wanted. They didn't force me to do engineering or medical or any of those things. And in the end, I actually ended up studying these microscopic fossils. If you look at the scale, this is 50 microns. Now, I study microscopic fossils, but I still study the dinosaur extinction event and what caused this extinction, which leads to the relevance of my research. My bachelor's, master's, and PhD were already explained to you by Dr. Shalini. I don't have to repeat that, but what makes my research relevant is, as I already mentioned, we may be in the middle of a mass extinction, and the world as we know it may not exist in a couple of decades or centuries. So all the more, I think it's important for us to study how living organisms have evolved, and what is their standing, and what are the vulnerabilities which can cause the next extinction, because it directly governs our future. So I think I will end it. So this is just a summary of all the journal papers. So if you look at the 1980s, there were about 3 papers on mass extinctions. 90s, you have a couple more, but less than 10. And more recently, you have over 300 publications discussing extinction. So it's becoming very relevant. Although I started off wanting to do pure sciences, it evolved into learning applied geology course, and then basically went back to applying the applied geology to pure sciences. But there is a social context to my research, which is understanding the fate of us as a species on this planet. I would like to end with a particular phrase that I picked out from Roger Newton's Why Science? Science and mathematics are amongst the highest achievements of human intellect. Centuries from now, let us hope that it will not be the ruins of the Pentagon in Washington that we leave behind us as equivalent of Parthenon in Athens. I expect that it will be our mathematics and science with physics at its basis, rather than war memorials that will command admiration long after we are gone. Thank you.
Thank you so much, Professor Janvi. It's been so fantastic to hear, and I would appreciate if you stop the screen and then we can have a live question and answer session. Already our audiences have put up a lot of interesting questions, and I'm so happy that we have such an enthusiastic, active audiences. Thank you so much, audiences, for putting all these interesting questions, which are very, very relevant. So to start with, we have a very first question from Shajia, and Shajia would like to know, Professor, your opinion on, especially it's a very, very difficult question, but yes, and also there is a time constraint because at 4 o'clock we have another event. on this INIAS's platform. So what is your opinion on our education system, especially in the light of critical thinking? Is our education system, do you think it is enough for critical thinking? And this very good question is from Shajia. Yes, over to you.
Okay, so I think I can only share my perspective. It's not for everybody, but I honestly felt that there was a serious lack of critical thinking and analytical thinking based on how we were. I mean, no offense to the schools, they are fantastic. The curriculums are devised in a very good way to give us a wide range of, exposure to different topics and sciences. But my personal experience and the transition was very difficult to make when I went for my PhD was um, I used to read everything and think that is final, that's fact, etched in stone, like just grasp it like it's sacrosanct knowledge. And changing that stance to people can be wrong, and I need to be on my guard and I need to assess the information that's being given to me. That transition was very difficult because I don't know, it just has to come from within yourself. And I think somewhere back to the question, it had something to do with the way the schools worked. We also have this culture of don't ask too much. If you ask too many questions, you're annoying, or no one says that, but the side effects of asking too many questions kind of encourage you to just shut up and not talk in class. So, but again, I call it a little subjective because it really depends on the students too. There are students who ask a lot of questions.
Yes.
So yeah, it's a mixed answer, but I think the education system does have a role to play.
Mm-hmm. Yeah, this is very interesting to know that yes, sometimes financial constraints, and especially if you look at the exposure of the students, in the urban area as well as the rural area, and the particularly for science, as you explained, the professor in your talk, that theoretical aspects as well as practical aspects. So if one reads theoretical aspects, for science it is not sufficient. One has to have that hands-on, and then the science becomes more interesting. Even it starts from children and the kids. So that facility, having that financial support or the experimental facility is very, very important. We have another very interesting question from Sudhanshu, and Sudhanshu would like to know that he has started 360 Research Foundation, especially to support creative and innovative people, and particularly students from Bihar, and which are coming from the backward state. So actually they have started from very ground level with students from BSc and MSc. So how can these can be connected to proper resources, and more can be brought out of that with the especially financial constraints, as I mentioned you before.
I don't know. I mean, this is again, it requires a lot of initiative from people who are more privileged.
Yeah.
And we would probably want to have people go to these places and at least summer camps or some interactive sessions. I'm sure NGOs are doing their bit, just like Sudhanshu said. And I don't know. I mean, it's such a big question. There is so much to cover that you cannot really give a one sentence answer. But one of the ways would be to actually, if you want to make this rigorous, then you can actually have institutes, make it mandatory for their faculty members or PhD students. I think IIT had a scheme like that, where you have to go spend some time in, any rural area of your selection, wherever you are comfortable, and interact with the local people and teach them science concepts that you can with not very heavy equipment or complicated contraptions. I actually have a student in ISER Pune. She actually works with science education, like devising new techniques to teach students. So they actually have a science teaching lab in ISER Pune, which is very cool. And I'm sure people like that who have a lot of drive and initiative can come up with simpler ways of explaining science to people in.
Wow, fantastic. Thank you, Professor. We have one more question from Muzamil Samad. Actually, he's from Jammu and Kashmir area, wherein, he says that a lot of exposure towards infrastructure is not possible. And we all know about, Jammu Kashmir. And he has done basically, what is better after doing BSc or MSc, doing direct PhD or integrated MS PhD, because I think in ICER and I think IISc there are a lot of options. So what is your opinion? Whether would you like to recommend for doing BSc, then MSc, and then later on PhD, or going for integrated PhD is a better option?
It depends on what you want to do, because not all disciplines offer all these possibilities. For example, 10 years ago when I did geology, the only route that you could do it was 3-year BSc, 2-year MSc, and then PhD. But it also depends on, if you can get into an ICER, I would say thumbs up, go for it, because my experience with ICER has been very good. And such schools can optimize time. They also allow you to, there is a 1-year research project which really helps you explore science in the area that you want. So their curriculum is really tuned to doing good science. So I would suggest, if science is what your goal is, then go for one of these institutes. Maybe I'm digressing. What was the question again?
Yeah, so especially in Jammu and Kashmir, the infrastructure facilities are not so good. So what would you recommend, going for a student to BSc, MSc, and then PhD, or
What stage is the student at right now?
Actually, BSc, the student has asked that integrated, because in our part of world we have the same syllabi, or BSc and masters, what is better. And currently he is doing MSc in chemistry, but he has observed that the syllabus is same as well at master level as well as bachelor level. The syllabus is almost same. So maybe the student is not finding it interesting, so like maybe that. So, or
yeah, so changing places is always good. My father tells me that, never do 2 degrees from the same place, or never do two milestones from the same research lab or place. It's good to get out of the same system and experience another one. So I think if someone did a BSc and is experiencing the same content in MSc and there is no growth, of course one can do self study if you are restricted to stay at home. Otherwise, I would say just find a different place to do your masters. And if that is not possible for whatever reason, there are always internship programs possible. So except, I mean, more recently because of COVID, it's a little difficult, but otherwise I know IITs, all these institutes, whether they are research institutes or educational ones, there is a practice of taking interns. So you can always go to one of these and get your hands-on exposure. Yeah,
yeah. Thank you so much, Professor. We have one more question. Especially, STEM or science is considered as a very difficult. I know that in Mumbai or big cities, because the kids have a very good exposure, very good facilities. Maybe the schools are better than in the rural area. So in the rural area, and I also do a lot of science outreach and talk to the students. So there is always, fear in the mind that science or technology or STEM field itself is a very tough, very difficult. So what do you think, kids can be um, attracted, or kids can be involved from the childhood or later on also at 12th standard? Many students, they go for art or other branches, avoiding this science branch, thinking that science is very complicated or very difficult, and we may not be able to handle it. So, and as you said, STEM is such a fascinating area where you have multiple job opportunity. And in fact, I would say, going beyond, STEM is life, because STEM, will make you think, very logically. It's life. In day-to-day life, everywhere STEM. So how or what could be the approaches through which we can encourage students, parents, kids, so that they there is a maximum number of students in STEM?
I think there are multiple layers to this problem. One could be the student's perception of his or own capacity. It could be the parents' perception of the student's capacity. It could be the parents' aspirations that they want to see through their kids. Like, mera beta engineer banega or doctor banega, you know. That is one problem. I think the perception of STEM is, or generally science and maths are difficult. Well, yes, I mean, if you don't understand or if you're not taught properly, they do seem difficult and daunting. I think I've experienced that too. I did not like this in school, to be very honest. I mean, I think I really picked up my interest for physics or math or whatever was in Xavier's when I went much later. It was during BSc that I, relearned many concepts that I should have known in school itself. So it's a combination of the teaching, what kind of teachers, what kind of student you are, your priorities at that point of time, so your capacity is a very small element to this bigger problem. So if the student is interested, he or she will always find a way of figuring things out. I mean, I'm scared of something is not the reason to not, do it. But if you do come to encouraging students to do STEM, yes, I think you can have these expos and science days and events like that, where
also in Maharashtra there are various organizations like Marathi Vignan Parishad who goes to the rural area and then they try to.
So you can actually have informal interaction between trained scientists and students aspiring to or who have no idea about science in a more welcoming atmosphere, not in the rigor of school or what to choose next kind of a situation. So that will help them relate to it as a way of thinking rather than something that they need to study hard for or they might fail. So when it's again, when it's about performance or where I will get after here or what kind of job, it completely takes the joy out of it.
Yeah, thank you so much, Professor Janvari. Actually, there are more questions, but I'm very sorry, audiences. We cannot take up more questions because we have another event that will happen on our INIAS's account. So therefore, we have to end. But what I can request, Professor Janvi, we will note down all your questions and we will try to answer via Professor Janvi, and then we can post it, on our a platform, some of the platform like INIAS or somewhere, so that these questions are also addressed. So it was wonderful, Professor, being here today with us and sharing a wonderful insight on science and opportunities for our students, for our research student also, how they can, critically think and choose and come on to the point. That's fantastic, and I look forward for your continuation mentoring association on another platform of INIAS, where we connect you with the students, researcher, where you share your experiences as well as research with our student, and they are empowered with your insightful knowledge. So thank you so much on behalf of INSA and Indian National Young Academy of Science, INIAS Mumbai chapter, and on my very own behalf, and Dr. Vivek and Dr. Vikram's behalf, I would like to thank you for your time and your valuable talk on the very important topic, which is actually important to students. Thank you so much, and a very big thank you to all the audiences, very active and enthusiastic audiences who have spent their time on the weekend, on Saturday. I know that you all are very, very interested. We all are scientists and we want to learn always, and therefore you are here today on Saturday. Spending your time and asking question is a very good skill. Thank you so much, everyone, for asking very beautiful questions. Stay in touch, stay safe, and see you on such insightful and encouraging, motivating talk on next Saturday with all of you. Thank you so much, and bye, everyone.
Thank you.
Thank you, Professor.
Thank you. Bye-bye.